This is the first problem for isentropic process. Please take your time to read and understand the problem. We are given the mass of the ideal gas undergoing isentropic process. In addition, the initial pressure and volume of the gas are also stated. The volume at the end of the process is given to be 3.6 cubic feet. Now, since the final volume is greater than the initial volume, and the process is stated to be isentropic, then we can say that the gas undergoes an isentropic expansion process. We are also given the specific heats at constant pressure and at constant volume of the gas. From this given information, we shall find the final temperature of the gas in degrees Fahrenheit, the final pressure in psi, and the change in enthalpy and change in internal energy in kilojoules. Now let's sketch the PV and TS diagrams. Since we know that we have an expansion process, then we can be certain that the curve in the PV diagram will start from the upper left and end at the lower right. Therefore, following this direction, then the TS diagrams will run from the top at state 1 and end at the bottom at state 2. Remember that in this problem, we're going to use the approximate solution in solving for the required parameters. Let's start with the final temperature. We can use this PVT relationship in solving for the final temperature T2. However, besides T2, there are two other unknown values in this formula, the specific heat ratio K and the initial temperature T1. Since we are given the values of Cp and Cv of the gas, then we can simply get the ratio of these two specific heats to get the value of K. On the other hand, the initial temperature can be found using the equation of state of ideal gases. In this formula, the only unknown quantity is the specific gas constant R. But by simply getting the difference of Cp and Cv, we can now compute for the value of the specific gas constant R. Substituting all the known values in our formula for T1, we'll get 394 Rankine as the value of the initial temperature. Now that we have found the values of K and T1, we can now isolate T2 at the left side of the equation and substitute all the known values at the right side of the equation. We'll finally get negative 243.1 degrees Fahrenheit as the value of the final temperature. Next, we're going to find the final pressure of the gas. We can now compute for P2 by using this PVT relationship. By isolating P2 at the left side of the equation and substituting all the known values, we'll get 10 psi as our final pressure. Next, we are going to compute for the change in enthalpy. Since we are instructed to use approximate solution, then we will use this formula to get the value of delta H. Substituting all known values in this formula, we will get negative 21.9 BTU as the value of delta H. Finally, we shall compute for the non-flow work. Remember that for isentropic processes, the non-flow work is just equal to the negative of the change in internal energy. By replacing delta U by its corresponding formula mCv delta T and substituting all the known values in the formula, we will get 16.4 BTU as our non-flow work. Now let's check our answers. Remember that the initial temperature that we computed is 394 Rankine, while the final temperature is 216 Rankine. This is consistent with what we have in the TS diagram, since T1 should be greater than T2. In addition, the value of P1 that was given and the value of P2 that we computed are consistent with what we have in the PV diagram, since P1 is supposed to be greater than P2 based on this diagram. Lastly, the sign of the non-flow work is also consistent with the direction of the PV curve. Since the PV curve goes from left to right, then the non-flow work should be a positive quantity, and this is what we have computed in this case.